In Chapter 16, we begin our discussion on the kinematics of rigid body motion. We're going to stick pretty much to motion in two dimensions, although a third dimension will come into play as we discuss rotations. We'll put the vector quantities of angular velocity and angular acceleration into the z direction, but all the other motions will take place in the xy coordinate system. So we're going to come across at least three different types of motion. We consider an unusually shaped object, something like a potato. If that object should move even through curvilinear motion from one point to another, and we examine 2 points on that object, point A and point B. If it's undergoing strictly translation, then the vector which points from A to B will be exactly the same in position 1 as it is in position 2. That is to say, the object moves through space, in this case the xy plane, but the orientation of the object remains unchanged. In the second case, my unusual shape might undergo a rotation, but no translation. So that rotation would be about a fixed axis. Now that axis might be on any portion of that object, but the idea is that it rotates around that axis. If I take one point on the object and I follow it during that rotation, the path of that point, call that point A, forms a circle of some fixed radius r about the axis of rotation. If I choose another point on the object, perhaps point B, it's also going to undergo a circular motion, and the circular motion of B and A will be concentric rings, both centered on the axis of rotation. In that scenario, you have rotation about a fixed axis, so that's an unmoving axis. It does not move through space. Now, if we combine any of those two, then we get what's referred to as planar motion, and that might be the same object moving through space and rotating. So in that case, point A, here and here, will undergo some sort of a translation. And if I look at point B, it'll also translate, but the orientation from A to B will be different. So you can see it's up and to the right over here on the left, down and to the right over here on the right. So the orientation, or the vector pointing from A to B, has undergone some change in and of itself. So consider a brick spinning on some axis. That would be rotation about a fixed axis. And if I choose a point on that brick, we're going to find that that point, as it moves around in that circle, has a velocity tangent to the circle, and the motion might be clockwise or counterclockwise. But a brick spinning and translating, so there's an axis of rotation, but as it rotates, it also moves through space. Okay, and so you can see this upper right-hand corner is now the lower right-hand corner because of that rotation. Oftentimes a brick will tip over, so at a later time this corner, which is also this corner, will undergo a very specific translation if it's tipped along, say, that lower right-hand edge. And we'll take a look at some of those aspects a little bit later on. So let's define a few of the parameters that we'll have as we look at rotation about a fixed axis. So we'll take a simple circle for now, rotating on a fixed axis, and here's a point P, and we'll say that the circle is moving in a counterclockwise direction. CCW stands for counterclockwise. If point P started at this orientation, which we'll mark in red, and then a little later on it's over in this orientation marked in green, then the line going from the origin, or the axis of rotation, to point P will have undergone some angular displacement. So we consider theta to be the angular position. Counterclockwise is considered to be the positive position, and that will also correspond to a positive k by the right-hand rule. Curl your fingers in the counterclockwise direction on your right hand, and your thumb will point out of the board or towards you. That's the positive k direction. Angular position is measured in degrees, rotations, revolutions, but most importantly, radians. This will be the more critical of those units. But even though there are units associated with angular position, it has no dimension, no length, no mass, no time. Omega is the angular velocity, and like a lot of angular parameters, they're going to be simply angular counterparts to parameters that we see in one dimension or three-dimensional length. So there's a linear velocity, there's an angular velocity. There's a linear position, x, there's an angular position, theta. And so the derivative of theta with respect to time, by definition, gives us the angular velocity. Now remember, theta, let's even say delta theta, that's going to be angular displacement. That has no dimension. It does have units, oftentimes radians, but no dimension. The denominator, on the other hand, has dimensions of time, units of seconds. And so angular velocity has units of oftentimes radians per second. That's the preferred unit, which is the same as seconds to the -1. If I take a derivative of angular velocity with respect to time, I get angular acceleration. And angular acceleration, very much like linear acceleration, is a measure of the change in angular velocity. Is the object spinning faster or spinning slower? It's a measure of the angular velocity with respect to time. It will have dimensions of seconds to the -2, or radians second per second, or radians per second squared. All of those could be angular acceleration. Then the point P, as this object rotates on a fixed axis, also has a speed associated with it. Notice this is a scalar quantity. Speed is equal to r, the distance from the axis of rotation to the point P, times omega. Keep in mind, omega and theta dot are the same thing. So the speed is r omega. That's often referred to as the tangential component of the velocity. In addition, there are accelerations for point P. A tangential is the more interesting one. This is a measure of speeding up or slowing down, and it's equal to the distance from the axis of rotation to the point P times the angular acceleration of the rotating object. So if it's neither speeding up nor slowing down in rotation, then point P is moving around with a constant speed, not a constant velocity. Direction of velocity is definitely changing, but with a constant speed. And since direction is changing, there must be something turning it, and that's where the normal acceleration comes into play. We've seen this before. V squared over r is the normal acceleration, oftentimes referred to as the centripetal, center-seeking acceleration. But v squared over r is also r omega squared, or r theta dot squared. Remember, omega and theta dot are the same thing. Now there are some other ways that I might write that tangential velocity. Let me just call it v, and that is a vector quantity. Can be a vector quantity. It's always going to be changing. And we saw that the speed, v, was equal to r omega, but it's more appropriate to write in vector notation omega cross with position. So omega now, that's angular velocity. What's the direction? Well, again, we use the right-hand rule. If it's counterclockwise, your fingers curl in the direction of rotation, your thumb points out. This would be in the positive k hat direction. Omega will always be, when we talk about planar motion, will always be in the positive or negative, in the case of clockwise rotation, k hat direction. R, of course, is in the ij plane. So the velocity vector quantity can be written as omega cross r. Remember, this is not the same as r cross omega. Cross product does not understand the commutative property. Acceleration, though, is really interesting. Acceleration is the derivative of velocity with respect to time. And so I have to use the product rule. So that's the derivative of the first, which is omega dot, crossed with r, plus this first, omega, crossed with r dot. But omega dot is just alpha, the angular acceleration. Cross that with r. And then r dot, and the parentheses here are very important, r dot is just velocity right here. So that's equal to omega cross r. And the reason the parentheses are important is that this is not the same as omega cross r. Associative property is not part of cross products. Omega cross omega, remember, is going to be 0 because any vector crossed with itself is 0. So this would go away to 0. So that's not what this is. But omega cross r, if r is pointing in this direction, omega, remember, is coming out of the board. I'll use a circle with a dot in the middle. Omega cross r then must be perpendicular to this. So I can write this as alpha cross r minus omega squared times r. So it's in the direction of r, but it's omega squared times that, and it's in the opposite direction actually, 180 degrees opposed to r. Alright, so let's take a look at a problem. Here I have a couple of belt-driven pulley systems. Here's pulley A, and it's got a radius of 100 millimeters, so r sub A is 100 millimeters, and it's moving with a rotational or angular velocity of 4 to 0.2 t radians per second. Now what we're interested in is the angular velocity of B here and C here. And the problem actually says at 5 seconds. We're not going to worry about that. We just want to do this generically. And the way that we're going to work this out is we're going to look at a point right here. I'm going to call that point 1. And I'm going to look at a point over here, and I'm going to call that point 2. Now both of these points are on this belt. And the belt, we're going to assume, does not stretch, does not slip. In that scenario, the speed at point 1 and the speed at point 2 must be the same. Well, the speed is equal to r omega. So the speed of 1 equals the speed of 2. But the speed of 1 is r, which is the radius of A, times omega of A. And the speed of 2 is the radius of B outer, so radius of B outer times omega of B. So that the radius of A, well, that's 100 millimeters times omega A, and the radius of B outer is 200 millimeters. Multiply that by omega B. Solve for omega B, and I find out omega B is equal to 1/2 omega A. So omega B equals 2 plus 0.1 t radians. In other words, I just took omega A and I divided that by 2. Now we'll notice the second belt is attached to this inner disk of the disk system for B, if you will. Now the inner disk and the outer disk are welded together, and so they're both going to have the same omega. So that means that the velocity of this point, call it point 3, the velocity of 3 is equal to omega B times r of B inner. Well, that's going to equal omega B times 100 millimeters. But that has to equal the velocity of this point, call it point 4, because they're on the same belt. The belt doesn't slip, the belt doesn't stretch, they must be the same. So that's going to equal 200 millimeters times omega of C. So that tells me that omega C is equal to 1/2 omega B. So omega C must equal 1 plus 0.05 t radians per second. And if I want to know what those values are at 5 seconds, I simply need to plug those into the equation. So the belt's the translational velocity is related to the angular velocity. And by using those relationships, I can find out how one pulley affects the others. Here's another problem. I have a disk, circular disk with a radius of 16 inches, and it's rotating about its center with a clockwise angular velocity. So omega equals minus 100 RPMs, minus because it's clockwise, so the minus sign indicates clockwise. 100 RPMs is going to be 200 pi radians. And RPM is a rotation per minute. So 200 pi radians in 1 minute, but 1 minute is 60 seconds. And so this is going to be equal, the zeros cancel. This is going to be 10 pi over 3 radians per second, or 10 pi over 3 seconds to the minus 1. And that's constant. And if that's constant, that means that alpha is equal to 0. I have a constant angular velocity. If the constant angular velocity is what I have, then a 0 angular acceleration also is what I have. Well, they're asking me for the velocity and the acceleration at a point on the right edge. That's this point right here. I can do it at minus 8 as well, but let's just do it for this point. So the position of that point, let's call that point A. So r sub A position is equal to 16 inches in the I hat direction. So to find the velocity of point A is equal to omega cross r, and that's going to be 10/3 seconds to the minus 1. Now it's a vector quantity, so it's in the k hat direction, and minus because it's clockwise, and I cross that then with 16 inches in the I hat direction. I go to my unit circle, there's I, there's J hat, and there's K hat. So counterclockwise, I, J, K. I have K cross I, and that's going to equal J. Since I'm going in the direction of the circle, that's positive. Of course, there's a negative sign there. So this would be equal to minus 160 over 3 pi. K cross I is J hat. Seconds to the minus 1 times inches is inches divided by seconds. So minus 160 over 3 pi inches per second J hat. J hat says it's going down. That makes sense. This is moving in the clockwise direction. So the velocity should be down. Now the acceleration is a little different story. This is equal to alpha cross r, but there is no angular acceleration, so that's 0, plus, and actually not plus, minus omega squared times r. So this would be minus, omega is a negative 10/3 pi, seconds to the minus 1, and I square that, times r, which is 16 inches I hat. And so this answer will be, and this is a minus sign, but that's squared, so that goes away, but this minus sign is not. So minus 100 pi squared over 9 times 16. There's no I or J in here at all, but I do have seconds to the minus 1, so it's inches over seconds to the minus 2, because I square seconds to the minus 1. And it's going to be in the I hat direction, negative I hat. That makes sense. The centripetal acceleration is going to be pointing in that direction, towards the center, center seeking. And so this is minus 1600 pi squared over 9 inches per second squared in the I hat direction. Now if I do these same things for this point at minus 8, 8, in that case r equals minus 8I plus 8J inches, and so my velocity is equal to minus 10/3 pi seconds to the minus 1 J hat K hat crossed with minus 8 inches in the I plus 8 inches in the J. And to do a vector cross product, I use a determinant, IJK, 0, 0, minus 10/3 pi seconds to the minus 1 minus 8 inches plus 8 inches, 0. So when I do that cross product, I'm going to get minus 80 over 3 pi inches per second. That's in the J hat, that's in the I hat direction. Okay, that comes from 0 minus that, so that's actually going to be plus, because there's a minus, it's going to be plus. And then when I do the J component, I get 0 minus, now the two negatives here and here will cancel to give me a positive, but I'm subtracting, it's 0 minus that, so minus, a minus is plus 80 pi, so I have 0 minus negative, and negative makes positive, so 0 minus 80 over 3 pi, but J by nature is negative, so it's going to be plus 80 over 3 pi inches per second. And since they're both positive, that must be up and to the right. But if I look at a point that's at minus 8, positive 8, negative 8, positive 8, it's going to be in that direction. That's up and to the right. So that agrees with this answer, which is up and to the right as well.